Brand new unit that we're starting today on electromagnetic radiation. There's two parts of this word that you're going to recognize already. Electro and magnetic. Electricity and magnetism. Clearly there's going to be a relationship here with electromagnetic radiation with electricity and with magnetism. And fundamentally it comes down to what electromagnetic radiation is and how it's caused. Electromagnetic radiation is pure energy that travels in a wave-like form. Now, what does that mean exactly? What is that pure energy, and how is that pure energy formed? How is it produced? Well, a guy named James Clerk Maxwell discovered that a changing magnetic field produces a changing electric field, and a changing electric field will produce a changing magnetic field. So here's the way it works. You got this field that's maybe an electric field. That will produce, let's go with just part of that actually. You get an electric field that looks like this. That will produce a magnetic field. I'm going to try to draw this perpendicular. Okay, bear with me on this because my artistic ability isn't the greatest. When I was 7 years old, everyone said, "Oh, he's a great artist. He draws like he's 8." Well, now I'm 42 and I still draw like I'm 8. And now it's not so good. When you're 7 and draw like an 8-year-old, that's really good. Okay, when you're 42 and draw like an 8-year-old, that's not so good. So bear with me on this. Okay, this is an electric field. Notice it's changing, right? Okay, it's sinusoidal. It's a wave. That produces, perpendicular to that on another axis, a magnetic field, which will produce an electric field, which will produce a magnetic field. Can you see what I'm trying to do there? Which will produce an electric field, and so on and so on and so on. So you end up getting the electric field producing the magnetic field producing the electric field producing the magnetic field, and so on and so on and so on. So that ultimately, what you get there is this transmission of two fields, sinusoidal in nature, perpendicular to each other, both carrying energy, going from one place to another. Now, what causes this? What causes these two sinusoidal electric and magnetic field waves that propagate, that move from one place to the other because they produce one another? What causes it? Well, fundamentally, what causes it is accelerating charges. That's it. It's as simple as that. All types of EMR. You guys saw the video. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. All types of electromagnetic radiation are produced in some way by accelerating charges. That's what it comes down to. Now, the exact mechanism by which each of those types are produced is different. Depends upon what kind you got. Depends upon what the frequency of that type of EMR is. But they're all fundamentally consisting of what you see up on the board and fundamentally produced by accelerating charges and fundamentally traveling at the same speed. We've talked about this speed before. We've said charged particles can't go faster than the speed of light. Nothing can go faster than the speed of light. What is the speed of light? In a vacuum or in air, pretty close to the same thing, 3.00 times 10 to the 8 meters per second, about 1 billion kilometers per hour. That's pretty fast. For perspective, the little lander that the European Space Agency just landed on a meteor out in space. You guys know how far that was away? A long way away. A long way away. It took 30 minutes for the radio waves to go from Earth to that meteor. 30 minutes. So if they wanted to control it, they would press a button. 30 minutes later, that signal would be received by that spacecraft. Now, if they wanted to see a picture back from that spacecraft, it would take 30 minutes to transmit that picture back. Light travels 1 billion kilometers per hour, but it still took 30 minutes to get to that spot. So that means that was about 500 million kilometers away. That's a long way away. Canada is about 6,000 kilometers wide. If light could go from Halifax to Victoria and then reflect off of the mirror and go back to Halifax, and then reflect off of another mirror and go back to Victoria, which of course it can't go all the way across the country, right? First of all, the curvature of the Earth is going to be an issue. Second of all, light is going to be absorbed by lots of different things, so that it's never going to make it that far. But let's say that it could. Okay, let's say it could go Halifax, Victoria, Victoria, Halifax, Halifax, Victoria, and so on and so on and so on. It would do that about 30 times return, about 30 return trips across Canada. Okay, Halifax to Victoria and then back to Halifax again. About 30 times in 1 second. That's how fast light travels. But yet, it still took a half an hour for light to go to this spacecraft that they landed on, a meteor in somewhere out in space there. Or a comet, I should say, not a meteor, a comet, right? So all of these types of rays, all of these types of radiation are the same thus far. They're all produced by accelerating charges. They all consist of an electric field that is perpendicular to a magnetic field, the electric field that produces the magnetic field that produces the electric field, and so on. They all travel at the same speed, 3 times 10 to the 8 meters per second. What's different about them? The frequency. And we'll talk about that in just a few minutes. We've briefly talked about this. They're caused by accelerating charged particles, which means, of course, what does that mean? Charged particle speeds up or slows down. Why does that produce electromagnetic radiation? Well, again, it comes back down to fundamentally what is electromagnetic radiation. You have a charged particle that's moving through the air at a constant speed. That produces an electric field. That produces a magnetic field. But if we plotted a graph of the magnetic field, it would be a constant value. Circular in shape, but not changing in value, not changing in strength. If we were to plot a graph of the electric field that was produced by this charged particle that was moving at a constant speed, once again, it would be a constant value. It wouldn't be increasing in magnitude or decreasing in magnitude. You're not going to get electromagnetic radiation here because this won't cause this, and this won't cause this. You still get an electric field and a magnetic field, but EM radiation has to be sinusoidal in nature or changing in magnitude so that it propagates, so that it moves, so that it's almost self-sustaining. So if this thing is moving at a constant velocity, this is what it looks like. But if this thing is accelerating, let's change this now to accelerating. It's either speeding up or slowing down. Then what you get is a magnetic field that's changing in magnitude. Okay, maybe it's speeding up, maybe it's slowing down. It's changing in magnitude like this. And all of a sudden, you got a magnetic field that's changing in magnitude. You also, by the way, have an electric field that's perpendicular to that, that's changing in magnitude. And then it goes back to the electric field causing more magnetic field, and magnetic field causing more electric field, and electric field causing more magnetic field, and so on. So now we've got electromagnetic radiation. Again, simply because the charged particle wasn't going at a constant speed, but rather the charged particle was accelerating in some way. So just like I said before, EM radiation, it's a transverse wave. I didn't say that before. Okay, difference between a transverse wave, what's the other kind of wave that you learned about in Physics 20? Transverse and longitudinal, right? Transverse wave is the wave that looks like a water wave. The longitudinal wave is that series of compressions and rarefactions, right? High density and then low density, and then high density and then low density. So it's a transverse wave that consists of sine waves, sinusoidal electric and magnetic fields, in phase with each other. What does that mean, in phase with each other? Well, when one crest, when you got one crest, you got another crest. Okay? One trough, you got another trough, and so on. So basically, these little things here that in Physics 20, I don't know if you remember the names of these things, we call them nodes. The nodes match up. The nodes of the electric field waves match up with the nodes of the magnetic field waves. They're in phase with each other. This is a little bit better of a diagram. because I've drawn these nice little lines in vertical and horizontal to try to illustrate which axis they're on. But it's still supposed to be the same diagram as I drew a few minutes ago, just maybe a slightly better version of it. You're always going to have one of these waves on one axis, say the x-axis, one of these waves on another axis, say the y-axis, and they're going to move perpendicular to both of those waves. So you've always got all three axes, x, y, and z. If one's on the x, one's on the y, it's going to move on the z-axis. If one's on the x, one's on the z, it's going to move on the y-axis. If one's on the y, one's on the z, it's going to move on the x-axis. Perpendicular again. Man, it seems like in magnetism, everything is perpendicular, isn't it? That last unit, everything always came back to being perpendicular. It does again. Now, this one's a little bit new. There have been lots of people throughout history that have thought electromagnetic radiation, or light, right, really prior to the last century, or 18th, 19th century, I should say, we had no concept of electromagnetic radiation per se. We knew light, right? Visible light, because we saw visible light. We could visualize visible light. We saw it every day. We didn't really have any concept of radio waves or gamma rays or whatever. And we certainly didn't have any concept of them being the same thing as visible light. But throughout history, there have been people that have argued that light, we'll say, just visible light, have been waves. Throughout history, there have been people that have argued that visible light are particles, just little chunks of light. And that debate has raged for some time. There's been periods of time where it's like, oh yeah, no, we're pretty sure it's a wave. And then there's been periods of time when, oh, I think this guy says, I think it's a particle, and so on. But it's never really been settled. Well, when Maxwell came up with his explanation of electromagnetic radiation, it was, for all intents and purposes, settled. If it consists of, EMR consists of an electric field wave and a magnetic field wave, then electromagnetic radiation is a wave. Now, there's evidence to support Maxwell's theory. There's evidence to show that Maxwell's theory is correct, that electromagnetic radiation is a wave. Now, do you guys remember what refraction means? We'll talk more about refraction later on this unit, but we would have briefly touched upon it in Physics 20. It's the bending of light, or the bending of a wave. Okay, when a wave goes from one medium to another, it changes direction. Well, light changes direction when it goes from one medium to the other. So the argument is, hey, if it does what a wave does, then it must be a wave. Let me just show you a quick little analogy to help you to understand that if you haven't seen this before. We got a parking lot here that's made out of pavement. And then over here we got a swamp beside the parking lot. And for whatever reason, in that parking lot we got a bunch of soldiers marching. Or maybe it's a marching band. It's a marching band, and they're all playing the electromagnetic radiation song with their instruments. If we look at these soldiers or this marching band from above, the line of them kind of looks like the crest of a wave. It kind of looks like a wave front, right? Well, let's say 5 seconds later, this guy, this soldier, he's walking forward, so he's up there. This soldier is up here. This soldier is up here. This soldier's up here. This soldier's up here, and so on, except for this guy. This guy is only right here. Why? Why hasn't he gone as far? Because of the swamp. He's now in a new material where he can't go as fast, right? So he can't catch up with all the other guys, or he can't keep up with all the other guys. Now, if we're looking at this from above, this wave front is going to look a little bit different. It's going to look like this. Let's go 5 seconds later. Now you got two guys in the swamp, one guy that's just entered the swamp. They're all going slower now. Draw the wave front, going to look like this. Okay, do it again 5 seconds later. going to look like this. Notice that these guys are all going in this direction, but as soon as they went into another material, a new medium, the swamp, the wave front goes this way. That's refraction. When a wave changes direction, when it goes from one medium to the other, when a wave bends, that's refraction. And light, all kinds of electromagnetic radiation will do that. They'll change direction or they'll refract when they go from one medium to another. That's refraction. If EMR undergoes refraction, and that's a property of waves, then EMR must be a wave. What about diffraction? Talked about this in Physics 20 as well. Remember when you got a couple of, even just one opening? Let's say it's a breakwater in a harbor to keep big waves from coming into the harbor and swamping the ships or the sailboats or whatever. The water waves are out here. They're big water waves, and they're coming in. They're coming in like this. But for the most part, they're broken by this concrete breakwater. But you have to have a place for the ships to come in, this little gap right here. But unfortunately, that also allows waves to come in. Water waves come in like this. But they don't just go in a straight line like that. As they go through that barrier, that broken part of the barrier, the opening in the barrier, they spread out. They're not bending. They're not changing direction. They're spreading out. That's diffraction. So refraction was the bending of a wave. Diffraction is the spreading out of a wave. Since that's a property of waves, and EMR undergoes diffraction, it really does, then EMR must be a wave, right? If it has a wave property, then it's got to be a wave. What about interference? We would have saw this real briefly again in Physics 20. You got water waves coming up like this. You got a little bit of this water wave coming through, a little bit of this water wave coming through. They spread out. They diffract. They interfere with each other. We get this interference pattern where the waves go through one another and we produce big crests and big troughs, constructive and destructive interference. That's a property of waves. But EMR undergoes interference. We can produce bright light by constructive interference, or we can completely cancel out light by destructive interference. If light undergoes interference, and interference is a property of waves, well then light must be a wave, or EMR must be a wave. What about this one, polarization? You ever heard of that? Let's say this is a piece of plywood, and that piece of plywood has a hole or a slit cut in it. We have a rope, and we're flinging that rope back and forth to produce a wave. You guys have done that, right, before? Okay, you fling a rope or fling something back and forth, and you see that wave, kind of that sine wave that's formed. You can fling it horizontally, you can fling it vertically, and fling it at an angle. Okay? You got this wave going in every which direction. But if that rope goes through this opening, there's only one component of that wave that's going to make it through. Okay, if you fling that rope horizontally like this, you can make a horizontal wave, but it's not going to go through there because you only have one vertical slit. If you fling it at an angle, you'll get a little bit of it going through, but only the Y component of it going through. If you fling it vertically, then it's all going to go through. We say that's polarized vertically. You only allow one component of the wave through. Does that make sense? Polarization is a property of waves, but light undergoes polarization. So if EMR or light does what a wave does, then EMR must be a wave. Right? Logically, if it does what a wave does, i.e. polarization, diffraction, interference, and refraction, then EMR must be a wave. All right, a couple of quick multiple choice questions, okay? Don't bother doing these on your phones and submitting them to me. We'll just do them as a group together, and we'll see what you know here. Okay, 97, EMR is produced by charged particles that are moving what? What do you got to do to produce EMR? Who says A? Traveling at the speed of light. Charged particles don't travel at the speed of light. Nothing travels at the speed of light except light. With zero acceleration, in other words, constant velocity. Charged particles traveling at a constant velocity produce an electric field. They produce a magnetic field. But what do we need to have EMR produced? Not just a constant electric and magnetic field, but a changing electric and magnetic field. So that's not going to work either, is it? C, a changing velocity. Does that work? Who says C? That's acceleration, right? The EMR is produced by accelerating charges. C is the answer. 105, Maxwell's work contained the new idea that an electric current produces a magnetic field. No, we could switch this question to make A the correct answer, but it wouldn't say Maxwell's work. It would say whose work? Oh, you guys just wrote a test on this yesterday. Who was it? No. No, the other one. No, not Henry. No, Faraday and Henry were the opposite of that, right? Faraday and Henry said that magnetism produces electricity. Oersted said that electricity produces magnetism. So that would be how we change the question to make A the correct answer. A current is induced in a conductor that moves across a magnetic field. That's Faraday and Henry, right? B is Faraday and Henry. C, an electric field that changes with time generates a magnetic field. Yes or no? Yeah, that one works for us here, right? C works for us. D, two parallel current-carrying wires exert a force on each other. Well, they do. It's a correct statement, but it doesn't answer the question. The answer is C there. Bailey, question? Occasionally. Yeah, occasionally. Yeah. When you see names, though, it's something like this, right? It's nothing too crazy. It's just a matter of, basically, who was it that figured this out? This is the last page that we'll show you today, which, listen, this is review. You already know this because we showed you the video at the beginning of class that gave you the entire electromagnetic spectrum. Remember? Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. You can't possibly forget those now, right? You can't possibly forget the order of those either. Before I found that song and started showing that song to my students, that works great for remembering the order of the electromagnetic spectrum. It really does. You get that in your head and you can't forget the order of them. But before I found that song on YouTube and started showing it to my students, this is the way that I used to show you how to remember the order of the electromagnetic spectrum. Let's start with visible light, because that's the kind that we see, right? And visible light consists of red, orange, yellow, green, blue, indigo, and violet. Start with visible light. Red on one end of visible light, violet on the other end of visible light. What do you think would be below red? Below red. Infrared. So we didn't really have to think too hard to recognize that infrared was just before visible light on the spectrum. Infrared is below red. And of course, above violet would be ultraviolet. Ultra means above, right? Higher. Higher than violet. Well, we got four left, radio waves and microwaves and X-rays and gamma rays. Here's the way I remember the rest of it. Hey, gamma rays sound like they're really, really bad for you. Well, they're going to be at the top then. X-rays are pretty close, so they're going to be in between ultraviolet and gamma rays. Then we got radio waves and microwaves. You're going to see tomorrow that the first kind of EMR that was ever experimentally discovered was a radio wave. So let's put that first. The only thing left is microwaves. In the end, we don't have to remember it that way now because we've got that song in our head that's going to help us to remember it. Okay, but we can also use some logic so that it makes a little bit more sense as opposed to just memorizing it. Before red or below red, above violet, and so on. Notice that I got written in here. We're going to rank these in terms of frequency, in terms of wavelength, and in terms of energy. Radio waves have the lowest frequency. They have the lowest energy, but they have the highest wavelength. So as you go from left to right, energy and frequency go up, and wavelength goes down from high to low wavelength. Tomorrow, I'm going to show you one more quick little thing, how each of these are produced, but then tomorrow we're going to give you some specific frequency ranges of these types of EMR that unfortunately you're going to need to remember. Okay, last thing for today. We're going to group these together into groups of 1, 2, or 3. Radio waves and microwaves are both produced by, well, accelerating charged particles, but specifically by oscillating electric current. What does that mean? Electric current that's going back and forth, back and forth. It speeds up, it reaches a peak speed, it slows down, it stops, and then it repeats the cycle in the opposite direction. Oscillating electric current. That's AC current. That's the current in our houses. You ever find you're driving on the highway and you drive underneath a power line, listening to the radio, and all of a sudden the radio kind of cuts out as you're going underneath that power line? Why does it cut out? Because that power line is transmitting AC current with a pretty high power. It generates electromagnetic radiation, specifically radio waves. So as you're going underneath that, you're trying to listen to the radio, but it's being interfered with by radio waves that are being produced by that wire. So it kind of cuts out, becomes kind of snowy. Radio waves and microwaves are produced essentially the same way by oscillating electric charge. Electric charge that's going back and forth, back and forth, back and forth. Infrared, visible light, ultraviolet, well, they're all produced by something that happens inside the atom. Transitions of electrons. From a high level to a low level. If you learned chemistry already, then you'll know something about this, right? Electrons can jump to a higher level, but they can also fall to a lower level. When they fall, they give off some type of EMR, normally infrared, visible light, or ultraviolet, depending upon the energy of the transition that takes place. We'll talk more about that in our last unit. X-rays are produced by, you know what, I used to go to the dentist office. Well, I still do go to the dentist office, but I used to go to the dentist office when I was a kid and wonder about this. They'd give you X-rays, and the hygienist would, this nice, pleasant, friendly lady, usually it was. Now you see more guys doing it, but she would, be nice, cleaning your teeth. She'd put this X-ray machine thingy up to your face, put these little things inside your mouth, and then she'd say, basically, are you ready? 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 It's not going to hurt. And then she'd run away. And I always used to think, like, wait a second. Why can I be exposed to this stuff but not her? Well, it turns out, right, that she's exposed to it 50 times a day, which is more of a problem than being exposed to it once every 9 months, which I'm exposed to it. X-rays do damage to us, right? They do. They do damage to healthy cells. But if you're exposed to them every once in a while, your body repairs itself so quickly that it doesn't really matter. But if you're exposed to them 50 times a day, well, then your body can't repair itself quick enough. How are X-rays produced? What they do is have an X-ray tube that accelerates electrons to an incredibly high speed, like 10 to the 7 meters per second. And then they smash them into a target. And they stop really, really quickly. As they stop, guys, 1 second here. As they stop really, really quickly, they decelerate. And that energy's got to go somewhere. The kinetic energy that these electrons have has to go somewhere. It goes into forming an X-ray. So we're going to say that X-rays are produced by rapidly decelerating electrons. Rapidly decelerating electrons. Finally, one last thing. We'll review this tomorrow. Gamma rays, incredible Hulk, right? Gamma rays are produced by nuclear decay. We'll talk more about that in our last unit as well. The idea that the atom, the nucleus, physically changes into something else. Kind of like alchemy, right? You're changing one nucleus into another kind of nucleus. In that process, sometimes you get gamma rays produced as well. All right, that's it for today, guys. We'll pick up there tomorrow. Okay, have a good night, everyone.